Dynamics of charged spherical clusters in a self-consistent field. This study investigates non-stationary self-consistent single-component charge systems that interact intensively with their field. Classical collisionless systems are considered, which are described by a kinetic equation utilizing motion integrals that remain valid in the absence of stationarity. The concept of the Meshchersky integral is introduced, used alongside the Kapchinsky integral. Furthermore, several quantum mechanical systems are examined. In this case, the study reduces to solving complex non-stationary Schrödinger equations. Only when the orbital angular momentum is zero does the studied system exhibit spherical symmetry. The conditions are identified under which the charge density remains spherically symmetric even when the angular momentum is non-zero. States with half-integer angular momentum present particular complexity. The psi-function has a spinorial nature. Solutions are found where the charge density remains spherically symmetric. Introduction. This study explores the behavior of charged particles moving together in a group, like electrons in a beam or clusters in a spherical formation. Understanding how these particles move is tricky because their interactions and motion are complex. Scientists often use the Kapchinsky model, which simplifies the problem by assuming the particle density stays uniform, meaning the force on each particle depends on how far it is from the center. An alternative approach, inspired by Meshchersky's work, doesn't require uniform density, offering more flexibility. The research also looks at quantum systems where particles influence their own electric field. Some special cases, like particles with half-integer spin, a quantum property related to rotation, show interesting behavior where charge density doesn't change with direction. Finally, the study examines a stable state where particles balance to opposing forces, one pushing them outward, inertia, and another pulling them inward, from their own collective charge. Surprisingly, this balance can happen even with a peculiar condition where the angular momentum, a measure of rotational motion, is mathematically negative. In simple terms, this work helps us better predict how charged particle groups behave, which is important for fields like particle accelerators, plasma physics, and quantum mechanics. Conclusion. This research explores how groups of charged particles move and interact when their distribution is perfectly spherical. Unlike simpler models, this study accounts for complex, changing forces where particles influence their own electric field. A key finding involves a special case where an unusual mathematical condition, negative squared angular momentum, allows the inward pull from the particle's own charge to balance the outward inertial force. The work provides exact solutions for these nonlinear, dynamic systems, including scenarios where quantum effects matter, such as particles with half-integer spin. These insights help better understand how self-sustaining charged systems behave, with potential applications in plasma physics, particle accelerators, and quantum mechanics. Essentially, it reveals how certain particle clusters can maintain stability under extreme conditions. This important article is authored by the following scientists. Thank you for watching this video. Please subscribe to our channel BP International to watch more videos in the fields of science, technology and medicine.